All right, let's take a look at problem 10. So 1 mole of liquid hexane at 10 bar, 50 degrees C, is mixed with 2 moles of hexane vapor at 250 degrees C and 10 bar. The process takes place adiabatically in a closed system at constant pressure. All right, so from this we have two things. All right, so I just want to make this page width. All right, so the two key pieces of information is we're told that the process takes place adiabatically and that it's taking place in a closed system at constant pressure. All right, so following the last two problems, all right, so if our process is taking place at constant pressure, all right, our first law is going to reduce to Q is equal to delta H. And then adiabatic, so if our process is taking place adiabatically, that tells us that Q is equal to 0, which in this case means that delta H is equal to 0. Alright, and so we're asked to determine the final temperature and if the system's a vapor-liquid mixture, report the masses. So let's do it. Okay, so let me start by characterizing my liquid. Okay, so this is going to be my liquid in this initial state 1 that we have here. And so we're told that I have, and actually let me just call it liquid rather than mess around with it too much. So I don't want to goof up the notation. So let me just use L. So let me just say that the mass of my liquid, right, we said we had 1 kilogram, and our liquid was at 10 bar and 50 degrees C. Okay, then we have a vapor. Oh, and it's not mass. We're dealing with moles here. So the number of moles of my liquid was equal to 1 mole. Then my vapor phase, the number of moles of my vapor, that's equal to 2 moles. We are also at a pressure of 10 bar. And the temperature of my vapor phase is 250 degrees C. Okay, so I'll keep my temperatures in degrees C just because a change in temperature in degrees C is equal to or equivalent to change in temperature in Kelvin. Alright, so the first thing I want to do is, our main working equation is going to be equal to, delta H is equal to 0. Alright, so delta H being the enthalpy of our final state minus the enthalpy of our initial state. So what I first want to do is I want to calculate the enthalpy of our, initial state, right? And what is our initial state? So we're going to have some liquid, right? Say it's in a beaker. So we know its pressure, temperature, and the number of moles present. So we can calculate the enthalpy of, say, the molar enthalpy of that liquid, then multiply it by N, get the extensive enthalpy of that liquid. Then we go to the vapor phase. Okay, we can calculate the molar enthalpy of my vapor. We know the number of moles in the vapor phase, so I can get the extensive enthalpy of that vapor. All right, so initially, my total enthalpy is, that enthalpy of the vapor plus the enthalpy of my liquid. Since I'm mixing adiabatically, the enthalpy of my final mixture, once I've mixed the two of these and they've equilibrated, has to be the same as that initial value. All right, and so once I have that value, and I'll know how many moles I'll have because I'll have a total of 3 moles, I can determine what phase I'm in and also the temperature as well. So let me go ahead and let me just make a note that for my mixture, all right, I know that I can even call this NM. The number of moles of my mixture is going to be equal to NL plus NV, which will be 3 moles. And it's also going to be at a pressure of 10 bars. Okay, cool. Now, as I calculate delta H, what we're given here in this problem statement is heat capacity data, and I'm assuming that I'll take it that I can assume that the heat capacity is constant since I'm not told otherwise, which makes my life a little easier. As we mix terms here, just note that the enthalpy of my liquid and vapor at saturation, which is at 165.7 degrees, right, that's in kilojoules per mole, where the heat capacities are in joules. So what I'll probably do is when I'm mixing terms, is I'll divide my heat capacities by 1,000, just so I can make sure the units work out. All right, so now if I want to calculate the molar enthalpy of my liquid, okay, what I'm going to do is, okay, I have a liquid, right? So I know that the enthalpy of my liquid at saturation is equal to this, okay, and that's at 165.7 degrees C. So what I'm going to do is I'm going to take this as my starting point, and then I'm going to calculate the change in enthalpy of going from a liquid at saturation, which is at 165.7, to my temperature 50 degrees C, so that I know the absolute value, quote and unquote, of the enthalpy of my saturated liquid at the same pressure, temperature of 165.7 degrees C, and get the enthalpy of my liquid state in relation to that. So what that would correspond to is HL, the enthalpy of my liquid, okay, is going to be equal to the enthalpy of the saturated liquid, and I'm going to write this as at my saturation temperature, plus Cp, right? So delta H is the integral of Cp dt, but Cp is constant, it's just Cp delta T. So it's going to be the heat capacity of my liquid times, okay, so my initial temperature, if you will, in this case would be, Tsat, since I'm working in relation to that. Well, no, I take it back. That's my initial temperature. My final temperature is TL. So this will be TL minus Tsat, right? It's just a little confusing because TL is actually less than Tsat. Okay, and I'll just be careful of my units. When I execute this, I'll divide the heat capacity by 1,000. That way, these are all consistent and in units of energy units of kilojoules. So likewise for the vapor, okay, HV will be equal to HSat V times Tsat plus CPV times TV minus Tsat. Okay, so let's flip over to MATLAB and let's do it. Okay, so I'll create a new script. Okay, and I'm going to start with the Tsat, and I'm going to work in Celsius just because it doesn't matter because I only have differences in temperature. Temperature of my liquid was 50 degrees C. Temperature of my vapor, 250 degrees C. So I have my temperatures. Let's get HSat L, and that is 22.645. I'm going to make a note that my unit of energy here is kilojoules. HSat V is 43.320. Okay, unit of energy there are kilojoules as well. Heat capacities, so CPL is 263.64. Right, 263.64, and I'm going to divide that by 1,000, right, so that I've got energy units of kilojoules. CP of my vapor, 226.34. Okay, and I'm going to divide by 1,000, so I can make note that my energy of unit here is kilojoules as well. Okay, so then I'm going to make note that when I compute my enthalpy of my liquid and vapor, the units will be in terms of kilojoules per mole. Okay, so my liquid was the first formula we had, which is HSat L plus CPL times TL minus TSAT. And we had HV is equal to HSAT V plus CPV times TV minus TSAT. Okay, and before I run it, okay, what I want is the enthalpy, okay, the total enthalpy of that starting system. Okay, and so maybe I could take this to be some state 1. Right, my total initial enthalpy would be equal to NL times HL plus NV times HV. Right, and if I wanted an intensive value, right, I could just divide by the total number of moles, which is 3. Right, it doesn't matter. Okay, so let me just do that. So we would know that N1 times H total is that. So if I wanted the enthalpy of my starting system, let's just do NL over NL plus NV times HL plus NV divided by NL plus NV, and that's HV. Okay, so my initial enthalpy is equal to what? Okay, well, let's see. So let me just have NL was equal to 1, and V was equal to 2. All right, make sure I'm right. 1 and 2. Okay. So I'll call it my enthalpy H1 is equal to NL divided by NL plus NV times HL plus NV divided by NL plus NV times HV. And that is equal to, so save this, H1 is equal to 38.9809. So H1 is equal to 38.9809. Okay, and that's going to be kilojoules per mole. If I had calculated the extensive value, right, that's fine, right, and I would know that that extensive enthalpy would be equal to the extensive enthalpy in my final state, and again I could divide through by the total number of moles to make it intensive. Where the intensive value comes in handy, which we'll use it next, is what phase do I have? Okay, so let me add another page. Okay, so we already said that delta H is equal to 0. All right, so H2 is going to be equal to H1. Okay, so I know the enthalpy of my final state. Here I've calculated on a molar basis. So H1's 38.9809. Okay, so what's key here is my enthalpy is 38.9809. So the enthalpy is between that of my liquid and vapor. So what that tells us is that we're at two-phase coexistence. Okay, so what's our final temperature? Our final temperature is 165.7 degrees C. Okay, so our final system, so our final mixture is at two-phase VLE at, so the temperature of my mixture is equal to my saturation temperature, and that's equal to, was it 165.7 degrees C. Okay, then the question is, what fraction's liquid and what fraction's vapor? And so just like we worked out the lever rule previously using specific volume, we can do exactly the same thing here using using enthalpy. Okay, and so the key is is that my total extensive enthalpy, okay, so I'll just call this H2 total, okay, it's going to be equal to N times H2, and that'll be equal to N times the enthalpy of my, and let me label this, N here being the number of moles in, say, my liquid at saturation, okay, times the enthalpy of my liquid at saturation, plus the number of moles in my vapor phase at saturation, times the enthalpy of my vapor at saturation. Okay. We divide through by N, the total number of moles, and we get that H2 is equal to, so N1 over N total, okay, that's just going to be my fraction liquid, and I'll just write it as XL, times HL sat, plus XV times HV sat, okay, and then I know that, N is equal to what I called NL sat plus NV sat, okay, so if I divide through by N, 1 is equal to XL sat plus XV sat, okay, so that's just a matter of what term I want to kill. So let me solve in terms of V. So NL sat is equal to 1 minus XV sat. So if I come back over here then, right, I can write H2, subscript 2 I was using. H2 is equal to 1 minus XV times HL sat plus XV times HV sat. Okay, I'll expand and collect terms. So H2 is equal to HL sat minus XV HL sat plus XV HV sat. So H2 then is equal to HL sat plus XV times HV sat minus HL sat. So that finally, let's solve for XV. X, add a subscript, XV is equal to H2 minus HL sat divided by HV sat minus HL sat. All right, and then finally, all right, once I have XV, I know XL is just 1 minus XV. All right, so let's solve. So if I jump back over to MATLAB, so I solve for H1. Okay, I know that H2 is equal to 1 minus H1. So then XV was equal to H2 minus what do I call it? Yeah, H sat L divided by H sat V minus H sat L. And then XL is just 1 minus XV. And I've got a typo. I have a typo because I cannot have a fraction of negative 2.9. It's got to be between 0 and 1. Oh, it's because I typed in H2 is 1 minus H1. Right? No, H2 is equal to H1. And I have XV's 0.79 and XL's 0.21. Okay, so my fraction vapor is 0.79 and my fraction liquid is 0.21. Cool. Hope that helps. Let me know if you have any questions.